All right, so starting today, we're going to get into chapter 12, where we're going to leave the two-dimensional world and kind of get into the three-dimensional world a little bit. We start talking about solids and some different aspects of solids, how to classify them, and then we'll get into the surface area and the volume. For today, we're just going to worry about naming and classifying them and identifying them. Okay? So we start off. What exactly are we talking about here? Some vocabulary. Some solids are what we call polyhedrons. Polyhedrons is simply a solid that has polygons for its faces, right? It's bounded by polygons. Faces are just the sides, right? So your faces are these guys here, right? And you have to kind of use your imagination a little bit, because in a three-dimensional world, trying to put that on a two-dimensional object, we start not being able to see some things. So there's obviously a face back here, there's one at the bottom here, and then one on the left-hand side here as well. Sometimes you'll see solids drawn, and I know you've seen this, with some dotted lines like this to try to show the pieces that you can't see. Okay, the dotted lines are usually the parts, the edges that you can't see, and that gets us to our next definition, which is edges. Which is edges. Okay, and the edges are just where two faces meet. Okay, faces are planes, if you want to think about them as planes. So anywhere where two faces meet is an edge. So there's an edge, there's an edge, there's an edge. I mean, they're all over the place here. Okay. And then last not least is vertex. Again, any corner in geometry is called a vertex. And so you get corners in a solid where three faces meet. Three or more faces meet, and you get a vertex. Okay? And obviously, we got a lot of vertices, a lot of edges, and a lot of faces. We need to be able to count them all up. Okay? Polyhedrons. Some of the solids we're going to talk about are going to be polyhedrons. Some of them are not. And we just talked about it. It's a polyhedron if all of the faces are polygons. So, for example, this guy is a polyhedron. Now, I know you've had a lot of this before. Do you remember what we call this guy? Yeah, this guy's a prism, right? A prism is bounded everywhere by a polygon. This guy right here is also a polyhedron. And we know that because the bottom down here is a rectangle, and then all the other faces here are triangles. So all polygons, this is a polyhedron, but definitely not a prism, because it comes to a point, it comes to a vertex up here. But you know this is called a pyramid. Okay? Some of the solids that we're going to talk about that are not polyhedrons. This guy's not a polyhedron because it's got some faces here that are not polygons. Those are circles. This guy is called a cylinder. And then you got this guy, which is a cylinder that comes to a point on one end, which we call cones. Last not least, this is not a polyhedron either, but a shape that we're going to talk about, and it's a sphere. Okay? Now, we're going to start getting into naming polyhedrons, right? If they're not a polyhedron, then they're going to be cylinders, cones, or spheres. And there's no way to name them differently, to identify them differently other than that. With polyhedrons, there is a way, right? With prisms and pyramids, what we do is we specify what type of prism and what type of pyramid. And that's because the bases can be different shapes. The bases for these cylinders and cones are all going to be circles. Okay? Spheres don't have a base. Bases are parallel and congruent faces. Okay? So cylinders and cones still have faces. Cylinders have two faces. They're circles. And a cone has one, which is a circle. But they're not polygons, so they're not polygons, so they're not polyhedrons. Polyhedrons have a bunch of faces, and they're all polygons. The bases, so these are the bases here, are defined as parallel and congruent faces. Now, in this prism here, there are a lot of faces that can be bases. This one and this one could be bases because they're parallel and congruent. The top guy and the bottom guy could be bases because those faces are parallel and congruent. The front and the back could be your bases because they're parallel and congruent. Okay? Now in pyramids, there's only going to be one base, and that's this guy here. Okay? This guy here is a rectangle, and it's the base. And the base in a pyramid is always the face that's opposite the vertex, the corner that it comes to. Okay? We're going to use those bases to identify the names of our polyhedrons. Okay? For example, some polyhedrons here. Or are they polyhedrons? Letter A, yes, this guy is definitely a polyhedron. All of the faces are polygons. Okay? So it's a polyhedron. How do we name it? Well, I know it's a prism, but if I look at the bases, and we can treat this front guy and this back guy as the bases, they're rectangles. And so we would call this a rectangular prism. Okay, we also want to come up with the number of faces, the number of vertices, and the number of edges. Okay? Number of faces. Well, just for right now, we're going to count them up. Right? One face, 2, bottom is 3, top is 4, left is 5, right is 6, so there's 6 faces. Vertices, every corner, 1, 2, 3, 4, 5, 6, 7, 8. There's 8 vertices. And then edges, 1, 2, 3, 4, 5, 6, 7, 8. And then we have to connect the bases, 9, 10, 11, 12. Okay? Now I'm going to keep doing this. 6 plus 8 is 14. And looky here. Interesting difference. We're going to see that some more in just a second. Okay? But there you go. Letter B. This is not a prism, it's a pyramid. So it's definitely a polyhedron because all of the faces are polygons. There's a hexagon at the bottom and triangles all the way around. Now it's a pyramid, not a prism, because it comes to a point. And like I said, the base is going to be that side opposite the point. There's 6 sides, so the base is in the shape of a hexagon. So we call this a hexagonal pyramid. So you can have triangular, rectangular, and then we just start naming, throwing an AL on the end of each of our base names. Pentagonal, hexagonal, heptagonal, octagonal, nonagonal, so on and so forth. Okay, this is a hexagonal pyramid. Number of faces. Well, we have the one down here that's a hexagon, and then we need a pyramid for every side of the hexagon to go to the top. There's 6 sides, so there's 6 pyramids, plus that one base is 7. Number of vertices. Again, we have to have all the vertices in the hexagon, which is 6. And then the guy at the top, so that's 7. And the number of edges. And so we need all the edges of the hexagon, 2, 3, 4, 5, 6. And then we've got to go to the point. 7, 8, 9, 10, 11, 12. 12 edges. If we add the faces and vertices together, we get 14. Ooh. Kind of the same deal as adding the faces and vertices of the prism. Interesting pattern developing here. Okay. Last but not least, is this a polyhedron? And you got to determine if it's a polyhedron first. Okay, and hopefully you're thinking the answer to this is no. And the reason why is because not all faces are polygons. This guy right here is not a polygon. So it's not a polyhedron. We don't need to worry about coming up with the name. I mean, we can name it. This is definitely a cone. But we don't have to worry about counting faces, edges, and vertices. Okay? All right? Now you try. You got 3 here. Stop the video for a second. Come up with whether or not it's a polyhedron. Name it. And then find the number of faces, vertices, and edges. Then start the video back up and see if you're right. Did you get this? Number one is the polyhedron. All the faces are polygons. There's triangles and even a square down there at the bottom. The base is a square, but a square is a rectangle, so we're going to name this a rectangular pyramid. Okay? Now there are 5 faces, 5 vertices, and 8 edges, and if you add the faces and vertices, you get 10, which is a difference of 2 still. That pattern's still kind of coming back. Okay? Number 2 is not a polyhedron because not all faces are polygons. This is not a polygon, this is not a polygon. Okay, I know this one is, but all of them have to be. Okay? And number 3 is a polyhedron. All of the faces are polygons. Now, the bases, again, bases are parallel congruent faces. The only 2 faces that are both parallel and congruent are these 2 triangles here and here. Since they're triangles, then we name the prism, this is a prism, it's got 2 bases, as a triangular prism. Okay? 5 faces, 6 vertices, which add to 11, and then there are 9 edges, so we have a difference of 2 again. That pattern is going to continue to happen. Okay? So there you go. That pattern is what we're going to talk about next. It's called Euler's theorem. And that's Euler, not Euler. Euler's theorem. Okay? Excuse me. Euler, who apparently sometimes had too much time on his hands, realized that in a solid, in a prism or a pyramid, the number of faces, vertices, and edges were related. And what we've just seen is the pattern that he found, which was, if you add the faces and vertices together, they're going to be equal to 2 more than the number of edges. Always. Always, always, always. Right? Just like this rectangular prism, we found the faces, vertices, and edges before. There was going to be 1, 2, 3, 4, 5, 6 faces. 1, 2, 3, 4, 5, 6, 7, 8 vertices. And I'm circled that down there because if you drew in the back edges that you can't see, then you'd find that vertex. And then the number of edges is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. And if you add 6 plus 8, it is going to be 2 more than 12. Okay, so Euler's theorem is going to always hold up. And that's your way of checking to make sure that you found all the faces, vertices, and edges. Okay, sometimes it can be tough to pick them all out. For example, if you wanted to take a look at this. So you're building a house, you've got this frame of the house, and you want to know how many edges there are. I don't know why, maybe you need to know it for some reason. Okay? Not all of those 2x4s are edges. Only some of them are. So, how can we find the number of edges? If we can find the number of faces. If we find the faces and the number of edges, the number of vertices, then we can find the number of edges. How many faces? Well, there's this one pentagon, 2, this is another pentagon. Then you got to have a face to connect them, each side, right? So 2, then there's 3, 4, 5, 6, 7. So 7 faces. How many vertices? Everywhere there's a corner, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? And then we can use Euler's theorem to help us figure out how many edges there are going to be. Because if you add the faces and vertices together, that's going to give us 2 more than the number of edges. So, there's 15 edges. Okay? So, use for Euler's theorem. All right. Last but not least for this guy is the idea of cross-sections, taking cross-sections. And you create a cross-section by intersecting a solid with a plane. So you're kind of slicing into a solid. And depending on what type of solid, And where we slide the plane, you might get different results, different shapes from your cross sections, different ways of dividing up a solid. Right? Cross sections are useful. The most useful cross section I can think of is if you take a cross section of a sphere. We've created a lot of things out of cross sections of spheres. Lenses, whether it's contact lenses, glasses, microscopes, telescopes, those are all cross sections of spheres. So if you take a sphere and then draw a plane through it, then you slice it and you get a lens. Okay? And there are other uses, right? Cross sections of cylinders can create, or were used to create drills, drill bits, things like that. So anyway, there are definitely some uses for cross sections. Now, like I said, where you slide the plane into the solid will sort of change what cross section you get. So to describe the shape of the intersection of this plane and solid, to describe the cross section of this particular cube would be to describe this purple section right here, where the plane and the solid meet. Since this is a cube, all of these sides are the same, and it doesn't look like it because we're trying to draw a three-dimensional object on a two-dimensional sheet of paper, but all of these are right angles. It's a cube, right? This is a box, which are made at right angles. So the cross-section of this particular plane and solid intersection is a square. Okay? But if you take the same cube and now you slide that plane to where it hits two edges, here and here, then now you've gone diagonally through this cube, and so the shape that you get is this right here, the purple shape there, which is not going to be a square anymore. Okay? This is a cube, so all of the edges are the same length. This is congruent to this, which is congruent to this, and 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 all the way around. Okay? But this guy right here, which is part of that cross section, is also the hypotenuse of this right triangle. And the hypotenuse is always longer than the two legs, right? So all of these sides are going to be congruent, but the hypotenuse is not going to be the same length. It's going to be different. So instead of getting a square, now you get a rectangle. Okay? What's also interesting is the solids that are left over, which is not being asked here, but I want to talk about it real quick. The solids that are being left over when you take a cross section, right? In letter A, the solids left over are still, again, two rectangular prisms, top and bottom there. Here, when you slide the plane diagonally, you've created two triangular prisms, because now you have a triangle here and a triangle here as the bases. So even the solids that are divided are going to be a little bit different, depending on where you slide the plane for your cross section. Okay? All right. And that's enough about cross sections, and that wraps us up. Okay? Homework's out in Canvas. Make sure you have that done by next time.